Alright, this is Ace Chemistry, chapter 4 on metallic bonding and also in intermolecular forces. So this will go pretty quick with metallic bonding. So metallic bonding is basically having the outer shell electrons being delocalized, meaning they will transfer throughout the atoms itself, and that's why they're good conductors, because you have complete transfer or sea of electrons that will take charges and go through, like copper wire. So outermost electrons kind of wander throughout the metal, causing the metal consists of both cations and negative charged electrons to like glue together. The free electrons can move rapidly in response to electric fields, so that's why you have a good conductor of metals. And the free electrons transmit kinetic energy readily, again, so it allows heat to conduct very easily. The layers of the atoms are hard and pull apart, are hard to pull apart of the electrons, holding them together. That's why metals are so tough. But individual atoms are not held by other specific atoms. They basically can slip through each other. That's why they're very bendable and ductile, that can be shaped in different ways. So they have high melting point and boiling points. That means they take a lot of energy to break the attractive forces between metals and delocalized electrons. They conduct electricity very well because of the delocalized electrons. The more delocalized electrons, the better conductor of electricity and heat. That's why copper is used pretty well. And they have high conductivity of heat because the movement of delocalized electrons can pass through from one metal to the next pretty easily. So that's pretty easy. Intermolecular bonding. This is where we get into strength of compounds and how their melting point and boiling points change depending on their structure and how they interact. So intramolecular forces are the bonds between themselves, so mostly ionic, covalent, and metallic. Strong covalent bonds are between atoms, but intermolecular forces are between molecules, and those are generally weak, specifically for covalent compounds. So the reason why they're weak is because it only has one type of force, and that's called van der Waals forces. They disperse temporary of positive negative charge. So they basically go back and forth between positive negative very quickly, and that's why they're so weak. There's permanent dipole, meaning there is a complete positive and negative charge between two atoms. Hydrogen bonding is a type of dipole that's stronger. That's only specifically for 3 types of atoms with hydrogen. So you can see here that the type of bond strength, you can see ionic is the strongest because it's a complete transfer of electrons. Hydrogen bonding is the second, specifically with water. And then you have dipole forces, which are just slightly weaker than hydrogen bonding, and then van der Waals forces are weaker than all of them. So for a bond to have different intermolecular forces depends on electronegativity. The more difference between electronegativity, the more ionic the compound is, and stronger the bond force. So here's the levels of different ionic electronegativity. So you can see the majority of mostly electronegative atoms are your nonmetals, with fluorine being the highest, and the lowest ones are your metals. That's why ionic bond is such a strong bond, because of the big difference between electronegativity. So as you increase the electronegativity, you increase the atom's attractive forces for electrons. So fluorine is the most electronegative, so it's going to want electrons the most. As you move it right across the periodic table, the electronegativity increases generally, and as you move up the group, the electronegativity increases as well. This is for nonmetals. So fluorine is the most electronegative element, with bromine being the least electronegative of the group. So electronegativity between covalent bonds have very similar electronegativity. That means they have equal sharing, and they're nonpolar substances like hydrogen, chlorine, bromine. When the differences in electronegativity starts to grow, they become more ionic, towards ionic, and become having dipole-dipole forces and or hydrogen bonding forces. So you can see here that things that have very little electronegativity has basically equal sharing between it. There's all symmetry here. Once you start becoming more and more difference in electronegativity, the distortion becomes greater. You start having asymmetric compounds. And then ionic is a complete transfer. That means there's no distortion at all between the atoms because there's no sharing of electrons. Okay. So when you have two atoms partially charged, you have a partial positive of an atom and a partial negative of an atom. And then you start having a dipole, which means you can have a polar substance. The more differences between electronegativity increases, the bond becomes more polar, and the degree of polarity is measured by its dipole moment. So the more stronger the pull between the atoms, the more dipole it becomes. So for example, here you have hydrogen chloride. Chlorine is very electronegative, with hydrogen being less electronegative, so the pull between chlorine is stronger. You can tell also with its valence electrons of 6 pairs here, or sorry, 3 pairs. And then H is a partially positive, where chlorine is partially negative. So the dipole moment has a direction towards chlorine, positive to negative. Here we have trichloromethane. This is a polar substance because there is unequal sharing. Chlorine is very electronegative with 3 atoms of chlorine, where hydrogen is more positive, so it's going to show a dipole moment towards the chlorine. But if we change the hydrogen with chlorine, then it's not equal sharing. Then it's equal sharing, and you have pulling all in the same direction, so it's nonpolar. So not one atom is pulling more than the other. Checkup number 9 on page 63. So you try these questions out, determine if it's polar or nonpolar, and we can discuss that. Any questions? So polarity and chemical reactivity plays a huge role. What is similar about these two molecules? They both have triple bonds. They both are between 2 atoms. But the main difference is that carbon monoxide is a polar molecule compared to nitrogen because of unequal sharing. Oxygen is a lot more electronegative than carbon, but nitrogen and nitrogen have equal pull, so that's why it's nonpolar, and CO is polar. So polarity plays a major role in reactivity and interactions because of the interactions between the partially charged ends of compounds, and this plays a major role in organic chemistry when we get to that soon, or this year. Van der Waals forces are temporary dipole-induced forces, meaning they go back and forth between partial positive, partial negative throughout the molecule. That's why they have weak forces. So a molecule that has temporary dipole, notice they will have partial positive, partial negative throughout the thing, and sometimes they'll be attracted, sometimes they'll be pulled apart because of repulsion, and it's induced by each other. So if one starts becoming more positive on one side, the other side becomes more negative, then that will cause another molecule to change as well. That's why they're very weak, because it's not a permanent dipole-dipole, it's a temporary. So van der Waals forces increase, meaning they will get stronger if you increase the number of electrons and protons, so the size of the molecule. As you get bigger sizes, they will have stronger van der Waals forces because there's more electrons to cause a temporary dipole-dipole. And increased contact points, so surface area. So the more surface area somebody has, it can cause a stronger van der Waals force. So here we have helium and argon. Helium has two valence electrons and two electrons. Argon has 18. So an argon atom is going to have a stronger van der Waals force because of the number of electrons. Therefore, it's going to have higher melting point and boiling point because it has stronger van der Waals forces because there's more electrons to cause a temporary dipole-dipole. So you can see here, visualization of the number of electrons, the boiling points are increasing steadily, and the enthalpy of vibration, meaning how well it can vaporize, increases as well. So stronger van der Waals forces. Enthalpy of so energy needed to change from liquid to gas increases because of the stronger van der Waals forces. So van der Waals forces increase with number of electrons, more energy needed to change from liquid to gas, and higher boiling point because of stronger van der Waals forces. Contact points. So you can see as the molecule gets strung out more in pentane compared to dimethylpropane, they have the same number of hydrogens, same number of carbons, but there's more contact in pentane than 2,2-dimethylpropane. So you're looking at, if there's more contact points, you're going to have a stronger van der Waals forces. So the stronger the van der Waals forces, the higher the melting point and boiling point is going to be. So you can see that pentane is at 36 degrees Celsius and dimethylpropane is in 10 degrees Celsius. So contact points, more van der Waals forces, higher boiling point. Alright, permanent dipole-dipole. So this is a complete positive or partial positive, partial negative charge. Oxygen is one of the most electronegative atoms, so it's always going to have a partial negative. Only when fluorine is around, you're not going to have a partial negative. But in this case, with carbon, carbon is partially positive, with oxygen partially negative. Polar molecules have a positive and negative ends due to unequal sharing, and they are going to have stronger forces than van der Waals forces because of the permanent dipole. So for example, butane is a van der Waals force because there's no permanent positive and permanent negative. Has a molecular weight of 58. Propane has propanone is a molecular weight of 58. So they have the same mass, but the boiling point for butane is 0 and propanone is 56 degrees, and that's because of its permanent dipole-dipole force. So more energy is needed to break apart propanone to boil compared to pentane due to its dipole-dipole strong force to keep propanone a liquid at room temperature. Van der Waals butane has very weak van der Waals forces, causing it to be a gas at room temperature. Alright, explain the difference between the boiling points of ICl, monochloride, iodine monochloride, and bromine, since bromine has a lower boiling point compared to ICl. Explain the difference using the properties of van der Waals forces / temporary dipole-dipole versus permanent dipole-dipole, and electronegativity of chlorine and iodine. Alright, strongest intermolecular force is hydrogen bonding, and that's only between HO, and HN. because of the sizes between fluorine, oxygen, nitrogen, they're going to have a stronger intermolecular force. So the radius becomes smaller, that means there's going to be stronger pull for electrons. So you can see here why ammonia molecules are going to bond better, have a stronger intermolecular force, is because the partial negative of nitrogen and the partial positive of hydrogen are going to make a intermolecular force of hydrogen bonds, which is very strong. Okay, you can see that with water as well. The electronegativity of oxygen is going to pull the electropositivity of hydrogen, and there's ammonia as well. So hydrogen bonds are very strong. They increase the boiling point of the molecule because of the radiuses between oxygen, nitrogen, and fluorine are smaller compared to, let's say, chlorine or phosphorus or sulfur. So the boiling points are going to be very dramatic. So predict a trend. It's going to be very, very high for HF and then drop down HCl, and then it starts to climb up back to bromine and iodine because of stronger dipole-dipole. So the weakest dipole-dipole is HCl. The strongest is HF because of hydrogen bonding. And then as you increase the size of your protons, you increase the the permanent dipole-dipole. Alright, try this one out. Explain the differences in the boiling points and the boiling points of ammonia, why it doesn't follow this trend. Alright, enthalpy change and vaporization, so boiling points and melting points. Water has a high hydrogen bonding force, so it's going to have differences between its boiling points and vaporization. So you can see here the change between group 6 hydride, so water, sulfur, hydrogen sulfide, and so forth. Same idea with HF. You see water is up here, and then it's going to dip down and then slowly climb back up. So water, H2S, then H2SE, and then H2TE. Surface tension and viscosity, same idea with hydrogen bonding. It's going to have higher forces because of the higher hydrogen bonding. So molecules do not tend to slide past each other. That's why you have higher surface tension and viscosity with water compared to other hydrides.